In a delta-connected secondary winding configuration, the secondary windings form a closed loop. This closed loop characteristic is fundamental to understanding current flow. When a load is applied to only one of the secondary windings, the resultant load current doesn't just stay within that single winding. Instead, it circulates through the entire delta loop. This means the load current will indeed flow through the loaded winding and critically also through the other two unloaded windings. The underlying reason for this behavior lies in the series connection inherent in a delta configuration. The three secondary windings are connected in series to form the closed delta loop. Consequently, any current introduced into this loop, such as the load current, must necessarily flow through all the elements of the loop, which includes all three windings. It's crucial to understand that the magnitude of the current in the other two windings will generally be smaller than the current in the winding that is directly connected to the load. The current divides within the delta loop. The current divides inversely proportional to the impedance of the paths. Because the impedance of the two unloaded windings in series will likely be higher than the impedance of the direct path through the loaded winding, the current splits accordingly. The magnitude of the current in each winding will depend on the specific impedances of the windings and the load. However, the key takeaway is that current will indeed be present in the other two windings even though they aren't directly connected to the load. This circulating current can have implications for transformer operation and protection. For example, it can contribute to losses within the transformer and needs to be considered in the design of protection schemes. When analyzing delta-connected transformers, it's essential to remember that the line voltage is equal to the phase voltage. However, the line current is not equal to the phase current. The line current is equal to the square root of 3, approximately 1.732 times the phase current. This relationship stems from the phase difference between the currents in the delta windings. This is different from a Y-connected transformer, where the line voltage is equal to the square root of 3 times the phase voltage, but the line current is equal to the phase current. When a single-phase load is connected to a delta-connected secondary, the current distribution within the delta windings is not equal. The winding connected directly to the load will carry the highest current, while the other two windings will share the remaining current. The exact current distribution depends on the impedance of each winding and the impedance of the load. To calculate the current in each winding, you would typically use circuit analysis techniques such as Kirchhoff's laws. These laws allow you to solve for the unknown currents based on the known voltages and impedances. In practical applications, it's important to ensure that the transformer is properly rated for the load and that the current in each winding does not exceed its rated capacity. Overloading a transformer can lead to overheating, insulation failure, and ultimately, transformer failure. Protective devices such as fuses and circuit breakers are used to protect the transformer from overcurrent conditions. These devices are typically installed on both the primary and secondary sides of the transformer. When selecting protective devices, it's important to consider the transformer's inrush current, which is the high current that flows when the transformer is initially energized. The inrush current can be several times higher than the normal operating current. Protective devices must be able to withstand the inrush current without tripping. The impedance of the transformer also plays a role in determining the fault current. The lower the impedance, the higher the fault current will be. The protective devices must be able to interrupt the fault current before it can cause damage to the transformer or other equipment. In addition to overcurrent protection, transformers are also often equipped with other protective devices such as temperature sensors and pressure relief valves. Temperature sensors monitor the temperature of the transformer windings and oil. If the temperature exceeds a certain limit, the sensor will trip a circuit breaker to energize the transformer. Pressure relief valves are designed to relieve pressure inside the transformer tank in the event of a fault. This can help to prevent the transformer tank from rupturing. Understanding the behavior of current in a delta-connected secondary is crucial for proper transformer operation, protection, and troubleshooting. The closed-loop configuration ensures that current will flow through all three windings, even when only one winding is directly loaded. Consider the scenario where a 480-volt delta-connected transformer secondary is supplying a single-phase 240 volts load from one of the phases. This is often accomplished by tapping the center of one of the windings to create a neutral point, effectively providing 120 volts on either side of the neutral. In this case, the winding with the center tap will carry a significant portion of the load current. The other two windings will also carry current, but the magnitude will be less than that of the winding with the center tap. The current distribution will depend on the load impedance and the individual winding impedances. If the load is increased, the current in all three windings will increase. However, the winding with the center tap will experience the greatest increase in current. It's important to ensure that the transformer is properly sized to handle the load and that the current in each winding does not exceed its rated capacity. The National Electrical Code, or NEC, provides guidelines for the installation and protection of transformers. NEC Section 450 covers the requirements for transformer overcurrent protection, grounding, and ventilation. It's essential to follow the NEC guidelines to ensure the safe and reliable operation of transformers. For example, NEC Table 450.3 and 450.3b provide guidance on the overcurrent protection requirements for transformers rated over 600 volts and transformers rated 600 volts or less, respectively. These tables specify the maximum allowable overcurrent protection device rating based on the transformer's rated primary and secondary currents. NEC Section 250 covers the requirements for grounding transformers. Grounding is essential for providing a low impedance path for fault currents, which helps to protect personnel and equipment from electrical shock. NEC Section 450.11 covers the requirements for transformer ventilation. Transformers generate heat during operation, and proper ventilation is necessary to prevent overheating. The NEC specifies the minimum clearances around transformers and the required ventilation openings. In addition to the NEC, other standards such as those published by the Institute of Electrical and Electronics Engineers, or IEE, provide guidance on transformer design, testing, and operation. These standards cover topics such as transformer insulation, winding design, and protection schemes. When working with transformers, it's essential to follow all applicable safety procedures. Transformers can operate at high voltages and currents, which can be lethal. Only qualified personnel should work on transformers. Before working on a transformer, it's important to energize it and verify that it is not energized using a voltmeter. Lockout-tagout procedures should be followed to prevent accidental re-energization of the transformer. Personal protective equipment, or PPE, such as rubber gloves, insulated tools, and safety glasses should be used when working on transformers. It's also important to be aware of the potential hazards associated with transformer oil. Transformer oil can be flammable and may contain harmful chemicals. Proper disposal procedures should be followed when handling transformer oil. In summary, understanding the current flow in a delta-connected secondary is essential for the proper operation, protection, and troubleshooting of transformers. The closed-loop configuration of the delta windings ensures that current will flow through all three windings, even when only one winding is directly loaded. The magnitude of the current in each winding will depend on the load impedance and the individual winding impedances. It's important to follow all applicable safety procedures when working with transformers. Let's further explore the implications of this current distribution. If one were to measure the voltage across each of the three secondary windings in a delta configuration with the load connected to only one phase, one would observe that the voltage across the loaded winding would be lower than the voltage across the two unloaded windings. This voltage drop is due to the impedance of the loaded winding and the current flowing through it. The voltage across the unloaded windings will be slightly high due to the circulating current and the transformer's internal impedance. This voltage imbalance can become more pronounced with heavier loads. Furthermore, the phase angles of the currents in the three windings will be different. The current in the loaded winding will be approximately in phase with the voltage across the winding, while the currents in the two unloaded windings will have phase angles that are shifted due to the inductive reactance of the windings. These phase angle differences contribute to the overall current distribution within the delta loop. When designing a power system with delta-connected transformers, it's important to consider the potential for circulating currents and voltage imbalances. These factors can affect the performance of connected equipment and can lead to increased losses in the transformer. To mitigate these effects, it's common to use transformers with matched impedances and to distribute the load evenly across all three phases when possible. In some applications, a grounding transformer may be connected to the delta secondary to provide a ground reference for the system. A grounding transformer is typically a Y delta transformer with the Y side connected to the delta secondary and the delta side grounded. This provides a low impedance path for ground fault currents and helps to improve the overall system protection. The size of the grounding transformer must be carefully selected to handle the expected ground fault currents. It's also important to consider the potential for harmonic currents in the system. Harmonic currents can be generated by nonlinear loads such as electronic devices and can cause increased losses and distortion in the transformer. To mitigate the effects of harmonic currents, harmonic filters may be installed in the system. Harmonic filters are designed to reduce the amplitude of specific harmonic frequencies. Another consideration is the transformer's tap settings. Transformers often have tap settings that allow the voltage ratio to be adjusted. These tap settings can be used to compensate for voltage drops in the system and to maintain the desired voltage level at the load. When adjusting the tap settings, it's important to ensure that the voltage is within the acceptable range for the connected equipment. The tap settings should be adjusted under no load conditions to avoid damaging the transformer. The transformer's nameplate provides important information about the transformer's ratings, including the voltage ratio, kVA rating, impedance, and tap settings. It's essential to consult the nameplate before working on the transformer. The nameplate also provides information about the transformer's insulation class. The insulation class specifies the maximum operating temperature of the transformer's insulation. It's important to ensure that the transformer's operating temperature does not exceed the insulation class rating to prevent insulation failure. The transformer's cooling method is also indicated in the nameplate. Transformers can be cooled by air, oil, or water. The cooling method affects the transformer's kVA rating. Oil-filled transformers typically have a higher kVA rating than air-cooled transformers. When installing a transformer, it's important to follow the manufacturer's instructions and all applicable codes and standards. The transformer should be installed in a well-ventilated area and should be protected from the elements. The transformer should be properly grounded to provide a low impedance path for fault currents. The connections to the transformer should be tight and secure to prevent overheating. After the transformer is installed, it should be tested to verify that it is operating properly. The test should include measurements of the voltage, current, and insulation resistance. Any problems should be corrected before the transformer is put into service. Regular maintenance should be performed on the transformer to ensure its continued reliable operation. The maintenance should include inspections for oil leaks, loose connections, and corrosion. The transformer oil should be tested periodically to ensure that it is free from contaminants. The transformer bushings should be cleaned regularly to prevent flashovers. The transformer should be de-energized before performing any maintenance. In conclusion, understanding the current flow in a delta-connected secondary is essential for the safe and reliable operation of transformers. The closed-loop configuration of the delta windings ensures that current will flow through all three windings, even when only one winding is directly loaded. It's important to consider the potential for circulating currents, voltage imbalances, and harmonic currents when designing and operating power systems with delta-connected transformers.